Hi guys, it's Mr. Rocco again, and this is the third and final video for this week, the week of the 14th. And in this video, I'm going to be talking about percent deviation or percent error. So we talked about measurement and we talked about observation inference in the other videos, right? Remember, a measurement is just an extension of your observation, trying to be more accurate with your observation. But of course, when we measure things, we know in real life that measurements always will have some form of error. For example, I could go outside, on a warm morning and say, I can make an inference. I could say, today I think it's going to get up to 90 degrees Fahrenheit. And the actual temperature later in the day never gets above 85 degrees. So I could make an inference. Let me pick a different color. Let's say I say it's going to be 90 today, Fahrenheit, but the actual temperature never gets higher than 85, right? So I made an error. I'm off by 5 degrees. I want to take that 5 degrees of error and turn it into a percent of error, right? I predicted that my temperature would be 90, but it was only 85. That 5 degree difference, I want to make that into a percent. So this is a very simple math equation, and I'll do a few examples to calculate percent error or deviation. The word deviate means to be off. If, let's say, you have a boxer, right, and they're going into a fight in the ring, and the other boxer punches them in the nose and breaks their nose in the middle of the fight. And then that boxer that has a broken nose ends up going to the hospital and gets an x-ray. The doctor might come in to talk to the boxer and say, hey, that other boxer broke your nose. You have a deviated septum. Right? The septum is the part of the middle of your nose there, the cartilage there, and it broke. Right? It's now split or twisted, and so the boxer has a deviated septum, so their nose is broken, is basically what they're saying. So deviation just means to be off. Measurements always have some part error, and these are just some reasons why we have error when we take measurements. Maybe you're just being careless. You're in science lab and you didn't get a lot of sleep, you had a rough night, and you're in the lab and you're just not really paying much attention. You're kind of half awake, half asleep, and you just don't really care. You're just kind of going through the motions, so you make a mistake that way. Or let's say you have an instrument but you don't know how to use it, right? The teacher went over, here's how you use this piece of equipment. You weren't paying much attention. You kind of drifted off there for a minute, and then you start using the equipment, but you're using it the wrong way, which then gives you a different number than you're supposed to get. So there's some error there. Or maybe you've used this instrument, hundreds of times. You know exactly how to use it inside and out, but the instrument's broken, right? And therefore you're going to have error. So these are just some reasons why you might have error when you're taking measurements. Now, there's also importance of error, I guess. Which one needs to be more accurate? Let's say a student in my class is going to have a back-to-school party. They got a little back-to-school picnic, and they really like Mr. Rocco. They say, hey, he's a cool teacher. I'm going to have a party at my house, a little picnic after school one day. So it's a Friday afternoon, and they stop in to see me in my classroom. Hey, Mr. Rocco, I'm going to have a back-to-school barbecue. Would you like to come? And I say, sure. I say, you know what? My car doesn't have a lot of gas in it, and I'm kind of broke this week. It's not payday. And I said, how far do you live from school? I have some gas, but I'm running kind of low. And I said, how far do you live from the school? And the student says, well, I live 10 miles away. I say, okay, I think I have enough to get to your house. And you're like, no problem. I have a gas can at my house. I can throw a couple gallons in your car if you want, and that'll get you the rest of the way back home. I said, sure. So school ends, I get in the car, I leave school, I head to the student's house, and I get 10 miles away, and I run out of gas. And I haven't reached the kid's house. The kid actually doesn't live 10 miles away. The kid lives about 15 miles away. So the kid underestimated their distance from school and made an error. But I ran out of gas. Is it the end of the world? Some might say, yes, be mad at that kid forever. No. Hold a grudge. No. So I call the kid a cell phone service, say, hey, I ran out of gas. You're a little further than 10 miles, and the car ran out. No problem. Kid gets in the car, or parents come down with the gas can, throw some gas in my car, and I'm good to go. Is it the end of the world? No. Small problem. My wife teaches second grade. She always tells her second graders, anytime you have an issue in front of you, what you call a problem, put it in two categories, right? We talk about classify. Big problem, small problem. So that would be, in my mind, a small problem. Ran out of gas. Could have been worse. Or let's go to now a big problem. Let's say you have a student who works, a former student of mine, and now became an engineer and works for NASA, and also became an astronaut. And this student is going to go to the moon and is getting ready. So they're down there at the Cape Canaveral in Florida, and they're fueling up the rocket, and they're about to get ready to go on a mission to the moon. And so here's the astronaut. He's getting ready to get on the ship, and the guy's putting the fuel in, and he says to him, hey, do I have enough fuel to make it to the moon, do my mission, and then enough fuel to get back to Earth? How many miles is it to the moon? And the guy filling up says, the moon's, roughly 230,000 miles away, and we put enough fuel, round trip for that. And the astronaut, no big deal. So the astronaut gets in the rocket, takes off, goes to the moon, makes it there safely, no problem, does their mission on the moon, and then gets back on the rocket and is about to come back to Earth, and is on the rocket's on its way back. The astronaut can see planet Earth in the window, and gets about halfway, 3/4 of the way to Earth, and runs out of gas, runs out of fuel. Guess what? Big problem, not small problem. That astronaut is not going to make it back to Earth. Right? It's going to end up coming in maybe too steep or too shallow, slingshot off the atmosphere, and that's the end of that astronaut. So that can be a huge problem, right? They didn't put enough fuel in a rocket ship. Or let's say surgery is going to happen. You have a guy, he's 55 years old, he's a chain smoker, and he's been smoking his entire life. Well, not his entire life, but let's say since he's about 20. So he started smoking at 20 and now smoking for 35 years, has had a couple of heart attacks recently, and is about to go under the knife for heart surgery, right? Do some bypasses. And so the guy's getting in there in the hospital, he's getting himself prepped and ready to go, and he's in the operating room, and the anesthesiologist going to put him out and start this big procedure, going to take hours. And here comes the doctor. And he looks like he just came right fresh out of college. And the guy looks up at him, the smoker, and says, hey, doc, is this going to go all right? How many times have you done this? And, of course, this young doctor said, well, this is my first time doing it by myself. I've usually been an assistant, but never been in charge of the main procedure. I'm fresh out of college, and I haven't done this very long, but don't worry, you're going to be in good hands. I don't think that guy's going to feel too good going to sleep in a few minutes and having this procedure done. So obviously accuracy needs to be pretty important, especially with heart surgery or any kind of surgery, right? A doctor needs to be on his or her game. Think about pilots. How much accuracy do they need, right, when they take off or they land an airplane, or a train conductor, or anything, a taxi driver, bus driver, right, when they have passengers on their bus. So accuracy is definitely going to depend on the situation you're in. So that's something to think about. Now, when it comes to percent error, this is the actual equation down here. The definition of percent error is up here. The amount of error expressed as a percent. So I'll go back to that example I gave in the beginning. I said, let's say I thought it was going to be 90 degrees today, but it only ended up being 85, actually. I'm off by 5 degrees. I want to turn that 5 degrees, that's my error, into a percentage. And this is the formula or equation that I would use. You take the difference between the measured and the accepted value. Now, the measured value was what I guessed. I thought it would be 90, And the accepted value, you can also call that the known value or the given value or the actual. Actual is usually a term they use a lot. Actual value. What was it actually, the temperature that day? That always goes on the top half of the fraction. So you find the difference. Now, it doesn't matter which one you subtract from which. In fact, you'll see sometimes in examples that I'll probably give you maybe on a homework or something, sometimes the actual number is higher than the number you guessed, right? In this case, I thought it would be 90, but it only ended up being 85 degrees. So I overshot. I overestimated. I was 5 degrees over what it actually was. But what if it was the other way around? What if I thought it was going to be 85 degrees and it actually got hotter than I thought and it got to 90? I underestimated. So it doesn't matter which one you subtract where. You can do you always want to do the higher number, obviously, minus the lower number. If I did 85 minus 90, I'd get a -5, right? When you subtract a small number minus a bigger number. So important thing here, just flip the number so that the big number is always being then subtracted, and you're taking away the smaller number. So your number is always a positive. So flip them around so you never get a negative. If you don't, and I've had kids in past years, they say, well, I got a -%. What does that mean, Mr. Rocco? A -% just means you underestimated. So you would just drop the negative sign. You get an absolute value. That's all a negative means. So you find the difference. Let me clear this. That goes on the top. Oops. Then, after you put that difference up here, which in this case would have been 5, right? 5 degrees. You put on the bottom half of the fraction the actual, and that's sometimes a common mistake. A student will say, well, I had two numbers. I had 90 is what I thought it would be today, and it only got to 85. Which number goes on the bottom? The actual number, which in this case, the actual temperature it got to today was 85. That number goes on the bottom, not the 90. So be very careful what goes on the bottom. The difference between the two is always on the top, but you divide by the actual number. So in this case, it's going to be 5 degrees, and then the 85, not the 90, would go on the bottom. You would divide that out. Now you can see when you have a little number divided by a big number, which is typically the case, you can get a small number here, big number here, you're going to get a decimal when you plug that into a calculator, point something. This is the third and final step, and very important, and that's to get it into a percent. You have to multiply by 100. So you're going to take the little difference, the small difference, little number, divided by the big number, equals some percent, or some decimal, I should say, and then multiply by 100 to get it into the percent. So let me pull up my calculator here, you'll see what I mean. So I had a difference of 5 degrees, so I'm going to plug that in the calculator first, 5. I'm then going to divide that by the actual number that day. It got up to 85. And that gives me a decimal. 0.058824. I then have to multiply that times 100 to get it into percent, and there's my answer. Typically in earth science, we round things to the 10th place, which hopefully you're familiar with your place values. You have tenths, hundredths, thousandths, right? If let's say this is a decimal. In earth science, you typically look at 3 values. So the first digit here after a decimal is the tenths. Then you have your hundredths, and then you have your thousandths. Normally we round most things, unless it says otherwise, round things always to the 10th place. So in this case, because I have 5.882, etc., when I want to round to the 10th place, this number, I look at this digit. Right, so you always looked at the number just next to the digit you want to round to. So because I'm rounding to the 10th, I look at the 100th place. Well, this is an 8, and I use the rhyme 5 or more, raise the score, 4 or less, let it rest. 5 or more, raise the score, 4 or less, let it rest. So that means because this is 5 or higher, this 8 becomes a 9. So this would now be 5.9%. And your unit, you call it unit, right? When you put a unit at the end, is going to be percent because that's what you were figuring out, a percent of error. Kids will sometimes make the mistake and say, this is 5.9 degrees. And I'm like, that's incorrect because you are figuring out your percent. You were 5 degrees off. But remember, you're using this equation to figure out what percent you were off. So this should always be a percent symbol over here, 5.9% off. Okay, let's do another example here. Let's say a student has a rock and they go to measure the mass of the rock, and they put it on a scale, and the student measures the mass to be 127.5 grams. And Mr. Rock comes back to the lab table and says, hey, great job, close. The actual value, or the accepted value, was 125 grams. So the student measures the mass to be 127.5, but the actual or accepted was 125. We want to use those numbers and that equation that I just showed you on the last slide to come up with the percent of error. So let's go to that. The first thing I do is I write down my equation, and on here I used, instead of writing out, let me go back. This was, let me clear this. This was called the measured value, and this was called the accepted value. So instead of writing measured and accepted, I just use M for measured, A for accepted. So here, that's what I did. So it's going to be the measured minus the accepted, and then this means divide by. Don't forget the accepted or actual goes on the bottom. I do all of that. Notice I put brackets. Kids will say, Rocco, why do you put brackets there? I put the brackets to know to do everything in those brackets first, so that I know the last thing I do is the multiply by 100. And then I'm going to plug things in. So remember the student measured the rock to be 127.5. So I got 127.5 minus 125. I divide that again. Make sure you use the same accepted value in the bottom. So you're only using the measured value up top. The kid measured it to be 127.5. That goes up top. But the actual value is used not only to find the difference between those, but also to then be used to divide by. So the 125 is always used, those numbers are going to be used twice, top and bottom, the actual. See, there's two A's, only one M. So, and then again, I put brackets there so I know I do everything first. And then the last thing I do is do that multiply by 100 to get it into a percent form. So I'm looking for my percent there, which ends up being 2%. And let me pull that up on a calculator so you can see that. So I like to hit the equal sign every time I do a function. And I would recommend you do that, only because when you're using calculators, I know sometimes some of you might have those fancy like Texas Instrument TI 80s or whatever they call them, TI 90s. I don't know what the new ones are called today. The ones that you can do all kinds of calculations, got a digital screen on it. You could, if you're careful, put those brackets in there, and you guys probably are better at those than me. And that would maybe make it easier. But I don't know if I'm sure you did learn in math class, there's, and correct me if I'm wrong, I guess, there's what they call this order of operations, right? You have add, subtract, multiply, divide. Multiply and divide, I believe, are done before add and subtract, right? And so you got to be real careful when you plug things into a calculator that the order of operations, because here you can see you're doing different things. You're doing a subtraction, you're doing a division, and you're doing a multiplication. So what happens is it might try to do the multiply 100 and the divide by 125 before it does this actual subtraction, and you'll get a totally different answer. And so you have to be very careful. So my recommendation is, well, first I would recommend you don't use those fancy TI calculators for earth science. Actually, simple is better. So if you have one laying around a house, just a simple basic calculator, that's the best kind. Like this calculator you see I pull up on the screen is a basic one. I would also recommend every time you do a step, you do it, let me clear this, you do it 3 times, because there's 3 functions you're doing. So you are, let me pull my calculator up. You are subtracting, that's the first step. You're then dividing, that's this line, right? Second step. And then you're multiplying. That's 3 steps you're doing to get the answer. That means 3 equals is what I would hit on a calculator. So what I mean is this. Let's do 127.5 minus 125.0. I hit the equals. That's once. I know the difference is 2.5. I'm then going to hit divide by 125.0 equals. That's the second time I hit the equal sign. And then I do that multiply 100 times 100 equals 2%, which I had covered by this box, but I'll pull that away. So I got a 2% error. So let me do it one more time. 127.5 minus 125.0 equals divide by 125.0 equals, there's my second equals, times 100 equals. So I hit the equal sign 3 times. I did this first function. That was an equals. I did this. That was second equals. I did the times 100, third equals. So try to get in that habit 3 times. Equals, 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 to make sure you get the right answer. Because I have seen students with those fancy calculators, like I said, they plug all the numbers in, they forget to use the brackets, and they plug it in, you'll get a totally different answer. And then the student comes up to me and says, Mr. Rocco, I didn't get 2%. I don't know what I did wrong. And I'll go through and show them what I do step by step, and then they'll say, oh, now I see where I made my mistake. So just be careful with that when you're using these, especially the fancy calculators. Like I said, my preference would be just to use the basic calculator. I'll do one more example. Now, this gentleman, we'll be talking about him when we get to the second unit, probably in October. Maybe even in this, it's October. His name's Eratosthenes. He was a Greek, he was a genius, geographer, astronomer. He did it all, jack of all trades. And he, actually, this is going back around 250 BC. He came up with an accurate circumference of the Earth, right? Circumference looks at the distance around the Earth. And he wasn't off by much. Considering what he used some basic geometry, and some of you maybe you're in geometry, maybe you're not. He used a rule called alternate interior angles. You might have learned this in middle school, where if you have 2 parallel lines and you have a diagonal, this line cuts across, this angle here is equal to this angle here. They call those alternate interior angles. He used that rule in figuring out the circumference of the Earth, and he used the sun and the shadow that the sun made on an object on the ground. So using a couple of basic things, he came up with the circumference of the Earth, and again, this was 250 BC, of 46,250 kilometers. That was his estimate, his measurement, Eratosthenes. This is the actual value we know the Earth is today. It's 40,074. So if we take his number, 46,250, and the actual Earth circumference, 40,074, we can figure out his percent error. And again, this was done over 2,000 years ago. So again, the first thing I would do is plug in, or write the equation, I should say. I have the measured value minus the accepted or actual divided by the actual. Notice again, I use the brackets to make sure I do everything in here first, and then I do the times 100. So his value, if you remember, I'll go back, was the 46,250. So I'm going to plug that number over here. I'm going to take the actual value away from his number. And then again, if you go back to the equation, oops, it's on the top. The A, that's the actual value, goes on the bottom, and then times 100. Again, when you subtract, and again, this will happen. If a student flip these numbers, if I put the 40,000 there and the 46,000, you can do that. You're still going to get the same difference up top here. You're just going to get a negative. So when you get a negative, just ignore that negative sign. That's all. When you do what they call absolute value, right? You know what the way you do this, right? If I had -6 and I had the absolute value sign, that's equal to just 6. So that's what I want to do with the percent. Just ignore that. But in this case, I didn't. I'm going to flip these back. And hopefully that didn't confuse you. And then I'm just going to use my calculator. Again, 3 times because I have 3 things I'm doing. I'm going to find the difference. That's 1. Then I'm going to divide. That's 2 equals. And then the times 100. That's 3 equals. Common mistake kids will do is they'll do the subtract and the divide. They'll forget this times 100 thing. And they'll end up with a decimal. And then they wonder where they made a mistake. So try not to forget that multiply 100 thing at the end. So let's plug this in. You get 46,250 minus 40,074. There's my first equals. So 6,176 was the difference. Divide by 40,074 equals. Now I got my decimal. And then don't forget the times 100. Times 100 equals. And again, we're science, we carry things out to the 10th place. That's one number. So if I have 15.41, I look at the second number because I'm going to the first digit. 1 means 4 or less, let it rest. So I drop the rest of this and just leave the 4. And my answer would be 15.4%. That's it. Which isn't that bad. And that was, I think, I think that was Eratosthenes' actual percent. Maybe this number's off a little bit, but either way, that's not a bad percentage, I don't think, considering what he used. And you might say, well, geez, Mr. Rocco, 15%, that's a lot. And it might be. For some people, like you say, well, if you're doing a lab, that might be a lot. Anything above like 10%. But for Eratosthenes 2,000 plus years ago, using the sun and some basic math, when people thought the world was flat, I don't think, he did a bad job there. Let's see, what do I have here? Oh, so there's a solution, just to show it that I did correctly. So I took the numbers, plugged them in, and I got that 15.4% to make sure I did the correct math. So I will post this video as well on Canvas, and that will be the third and final video for this week. So again, go back, make sure you watch all three, pause, rewind, whatever you need to do to help you with the assignments. Again, there'll be a homework that goes with each video, one for each video. Those homeworks are due at the end of the week by Friday afternoon, 3 p.m. So I'll post these on Monday morning, the 3 videos. I'll try to get into a routine here. Monday morning, get the videos. Friday afternoon, the homeworks. I'm also going to post a lab. The first lab is an observation lab, which we talked about in the first video, chocolate chip cookie. I'll make a very short video on that, what you're expected to do. Remember, the lab, you have 2 weeks. So I'll post it Monday morning on the 14th, but you'll also have the week of the 14th and the week of the 21st to complete that lab. That lab will be due the following Friday, which would put us at, what would that be? 25th? I think 25th. Yeah, something like that. So look for that lab to be posted on Canvas as well. Okay. Thank you guys. I hope you're doing well. And I'll talk to you soon.